Hello and welcome back. My name is Umar Harun Malik. On behalf of Apex and CBPA, I welcome you all again back on the Module 4 of EMTP. Well, we all know about Apex now. This is the fourth session, but I'll repeat because it's important. Apex is the Association of Power Exchanges and it has member countries now 45 all across the globe. Apex, one of the main missions of Apex is to actually increase the knowledge of the participants on learning about electricity markets. So EMTP is one step towards that direction. The presenter for today is mainly Mr. Etazaz. Etazaz has over 13 years of experience in the power sector, especially in transmission. So he has been doing the studies such as load flow, short circuit, and stability. People who knows transmission knows that. As you know, my name is Umar Haroon. I am head of market operation and development at CBPA. I'm also at the board of Apex. Well, the important thing is that I'm also the course director of this very important program. What we have covered today are the first three sessions. We Today we are covering on session number 4, which is on the top right of your screen. I'll talk about that in a bit in the next slide. However, please make a note that we have got feedback from several participants about the session which is on electricity markets, design and operations on 18th of December. Well, that program we need to change that date because several of our participants will be on leave on winter vacations. So on 8th of January, most likely we will be running this fifth module. But expect an email from my team in this regard, and we will fix the date and time. So this will be the first Monday, I guess, of January, which is 8th of Jan. But it depends really. If you feel that 8th of Jan will not be suitable for most of the participants, we can even relay this forward further 1 week ahead. So we can, start it even later. But you expect an email and please provide us a feedback. Maybe with your feedback, we'll finalize the date. But this session is going to happen in January, not in December. I'm talking about session number 5. So apart from this, the contents that we have covered so far under session 1, 2, and 3, in first session, it was setting the perspective, in which we covered the general idea of markets, the high level concepts. We also discussed certain markets. We can compare and contrasted why different markets are different. So we gave the perspective overall. The second section was a deep dive into demand generation and ancillary services, in which we try to understand that what are the different characteristics of demand and how generation is brought into the system to meet those characteristics. Ancillary services were also discussed at length so that the participant can understand that what ancillary services are, who provides them, how they're compensated, and so different dimensions of ancillary services were discussed as well. In session number 3, economic optimization of power system was discussed. Mainly the topics which were covered, they included unit commitment of the existing generation supply stacks, and we also discussed the second important thing was how the new capacity investment decisions are made. So several concepts were discussed with numerical examples. Well, a few words about today's session. Today's session is about transmission. So you have load on one side and you have generation on the other that connects. The thing that connects, we all know, are the wires, which is the high voltage wires that transmission. Transmission, as far as market design is concerned, they take a very important place because it is I would say, you can say this is a marketplace on which the trading takes place. So the constraints, the limits on capacity limits on the transmission network, they do affect and impact the market design. And the trainer today will tell you some details about it. I'll not go into detail right now. So they affect the transmission, the design of the market, and they also affect the behavior of the market participants. So it is very important that the participant do understand from a conceptual level at a very high level about different type of constraints, including not limited to thermal limits, angular stability limits, and voltage stability limits. Uh, for some of the participants, these words would have sounded very remote and alien, but believe me, the trainer today has made several perfect examples for you. So he will try to make things easy for you so that everybody understand these concepts even though they don't have engineering background, so they can understand these concepts. So to do this, we have made several numerical examples. We have may use certain best, I would say, best of the tools which are available that we are using for transmission studies to make certain models, and the outputs of the models will be discussed with you so that you understand these concepts and their impact on the design of the market and how the behavior of the participants is impacted. Well, with this introduction, I'll leave it for the instructor to go into details with you. Well, in today's session, do expect that we have practical exercises. There will be one spot quiz for you, and there's online assignment in today's session for you as well. So you will enjoy these exercises today. I'm sure that you will have a great time. At the end, as usual, we will have a Q&A session. It depends that if you have questions, you can post them uh, on on the tool itself on Microsoft Teams chat box. One important thing that I want to apprise all of you about is that we have received some feedback because the time that we have selected for this training doesn't suit everybody, because it is 2 p.m. GMT, which means that people in US, they uh, are about to join their offices. People in Turkey, we have participants in Turkey, they say that we are on the way to home. So certain people in Malaysia, participants, they say that it's very late, let's say like uh, 1 a.m. in the morning that your session ends. So in Pakistan, it's like 7 p.m. So it's very difficult for us to adjust a suitable time for a global, let's say, participation. So we understand that it is difficult for people to attend the session. However, what we have decided now is for each and every session, the certificates will be issued by session. So, for instance, if somebody has attended only two sessions out of four, so we will also issue, the Apex will issue attendance certificate for session one and two. However, if there is a reason and you communicate to us that reason, that why you were unable to, apart from that timing difficulty, you were unable to join this session. So what you need to do is to take our YouTube video out, download it, or just see it online and attend the quizzes. For that, you need to send us an email that why you were unable to attend the session live. And number two, you can request in that email, if that request is approved, to forward you the quizzes. So you just do the assignments and quizzes, and we'll mark your attendance by trusting you and send you the certificate from Apex as well. So thank you very much, everybody. I hope you will have a great session of learning today. So let's start it right now. Thank you.
Hello everyone. I am delighted to welcome you to the fourth session of our electricity market training program. It is truly heartening to see participants from various corners of the globe joining us for this enriching learning experience. Seeing this passion in the participants motivates us further in this endeavor, and we hope that we can collectively attain new heights. So, ladies and gentlemen, without further ado, let's discuss our main topic of the day, which is transmission. But before we do so, there is a very important question that comes to our mind, that why is the study of transmission important when we are studying the electricity markets? Well, one of the primary driver of this is the fact that transmission infrastructure serves as a crucial enabler, acting as an interface for exchange of power between the buyers and the sellers. Transmission is a backbone that ensures that power can seamlessly flow from where it is generated to where it is needed. In this way, it creates a foundation for a robust and trustworthy marketplace. If the transmission system is unable to carry power from where it is produced to where it is required, the trust of the market participants in the market substantially drops. Secondly, relation between the market design and transmission system is quite intricate. The market design takes into account the practicalities of the transmission. For example, the markets where transmission constraints are more prevalent, central dispatch model is a popular choice of the market designers. This is the case with our market model in Pakistan as well as the markets in the United States. Apart from this, the products that are launched in the market are also closely tied to the transmission requirements. The very structure of what is bought and sold is influenced by the capabilities and limitations of the transmission infrastructure. For instance, the National Grid ESO is preparing to launch a stability market in UK with the products including dynamic voltage support as well as inertia. Now both these things are required by the transmission system because they have a very strict net zero target. Lastly, there is a direct correlation between the transmission constraints and the behavior of the market participants. This is reflected in their bidding strategies and the risk management measures they adopt. In the next session, coming next month, when we'll be discussing the markets, we will discuss some of these measures which include the financial transmission rights and the physical transmission rights. So now let's discuss in detail what we would study today. We have quite a diverse list of audience. We have people from the legal backgrounds, we have people from the financial and the commercial backgrounds. We have people who have not really taken power system in their undergraduate courses. Now, since power transmission is a specialized topic dedicated to the electrical engineers, we will have to build the basic understanding of a few ideas, and from them we will discuss more complex and understand more complex concepts. So in order to do so, we must set a goal. That goal for today is understanding what the transmission capacity limits are. Now these transmission capacity limits are primarily limited by three factors. Those factors are the thermal limits, the voltage stability limits, and the angular stability limits. Now, our focus today would be to understand all these three limits. In order to do this, we must refresh our knowledge of some very basic concepts which will pop up here. We will have to understand what the power triangles are. We would need to understand what the per unit system is. We will need to understand how the transmission lines are modeled and how they behave. And one important consideration in their behavior is the idea of surge impedance loading. So in order to reach our goal today, we will have to understand these four topics. While to understand the first topic, the power triangle, we will have to understand what the phase difference is, we need to understand what the active power is and the reactive power is, and how these the active and reactive power are linked with the apparent power. So we will start from here and we will reach our target today by the end of the session, that we will have a good understanding of what the transmission capacity limits are. Also, to understand how the power system behaves and understand these limits, we would use a popular power system simulation software in which we will model these transmission capacity limits. However, the purpose would be to see the software for the results and not how the system is modeled in itself. Now, ladies and gentlemen, let me show you what a transmission system looks like. The whole power system is shown in a form of a diagram in this slide. To the left is a generation station which typically generates power at the voltage of 11 or 13 kV typically. Now this voltage is stepped up to the transmission level using the generation step up transformer. The generation step up transformer transforms the voltage up to 765, 500, 345 kV, 230 kV and 138 kV are other design voltage choices. These voltages are used as per the need of the system planner, and there is also a provision of 220 kV as well as 132 kV transmission standard. which is also utilized in some parts of the world, including Pakistan. This power from the generation step up is carried to the distribution on the right using transmission lines. Some consumers that take power directly from the transmission level are connected directly to the transmission system, while most of the consumers take power from the discos, which are shown here, through what are called distribution feeders. Now let's discuss the types of power transmission systems that are used. Firstly, we have the AC transmission system, which is more of a legacy power transmission system, while the second type is a more recently adopted DC transmission system. In the AC transmission system, the voltage and current change their direction in every one cycle, while in the DC transmission system, we have a constant voltage and current that are supplied, and the DC voltage or current does not vary with time, as can be seen from these diagrams. Now let's discuss some features of the AC transmission system. The AC transmission system comprises of step up transformers and step down transformers. Apart from the step up and step down transformers, there are certain circuit breakers as well as things like potential transformers and current transformers that are used to measure the currents that are flown in the AC transmission system. Now, a very important characteristics of the AC system that it was made more popular in the 19th century, and therefore it is a mature technology. And because of this maturity and the fact that it has been in use for over a century now, there the products that are used in the AC transmission have a substantially lower cost, which means that in order to install or operate a AC transmission system, less of a cost is required. The infrastructure used in the AC transmission system is also quite simple to manufacture and simple to use because of this maturity. Now let's see the characteristics of the DC transmission system. The DC transmission system takes input as power in the traditional AC form. It then steps the input power up to the level for which the HVDC system is designed, and then this is where it converts the input AC power to DC power, which does not vary over time, using device called rectifiers. Once the DC voltage is obtained from the rectifier, it is transmitted over the HVDC lines to the receiving end, where the devices called inverters convert this DC power into the AC power. This AC power is then stepped down using the step down transformers and fed into the traditional AC networks. Now, as we can see here, the DC power does not vary with time. This makes it time invariant. This is probably the biggest advantage of the HVDC systems, that when the power is time invariant, it does not depend on frequency. So what does it mean is that if from one end I have power coming at 60 hertz AC, while on the other side I have a system which is connected to a 50 hertz AC system, The DC's line can connect these two systems, something which is not possible to achieve using the AC transmission. Therefore, it provides better interoperability between the two systems operating at different frequencies. Apart from this, the DC lines become very efficient in terms of losses when the power is transmitted over very long distances. And since these AC DC lines uses rectifiers and inverters which are primarily composed of the power electronic equipments, we can build better control. We can have better control over active and reactive power it can produce. However, a major feature of HVDC lines is the fact that since the rectifiers and inverters take quite an investment to install, it has a higher installation and operations cost. However, if we are delivering this power over very long distances, it becomes cost effective. But for medium to short distances, DC line comes with a very high price tag. So our next slide compares the cost of building an AC system with a DC system, right? So on our y-axis we have the cost of building one of the two systems, and on the x-axis we have the distance for which this system is being built. Okay, so as we see from this diagram, the cost of building the DC grid station is lower. Okay, while the cost of building the DC converter station is higher. But as the length of the line increases, the cost of building the AC line increases more sharply compared to the cost of building a DC line. This is because of the fact that the AC transmission has to be done in 3 phases. Therefore, the cost of conductor rises. Okay, so let's say that when we reach a distance of 800 kilometers, which is more like a standard, the cost of building the AC line and the DC line becomes the same, which means that for all distances over 800 kilometers, it is more optimized to build a DC system than an AC system. While for a system that spans less than 800 kilometers, the cost of building the AC system is more optimized. By the way, this is the case when we are talking about the overhead lines. Okay, let's just assume that we have to build overhead lines that spans 1500 kilometers. As we can see here, it is better to build or more optimized to build a DC system as compared to the AC system, which would be somewhere here with a higher price. So this is the amount of money that we would save if we are building a DC system. Okay, but when we are considering the under sea transmission lines which we have to build when we are connecting our we are connected our offshore wind farms to the power system, then the cost of building the submarine cables has a break even point of 50 kilometers. Okay, so this means that when we are building our submarine transmission lines for, let's say, our wind farms that are offshore, then if the distance is over, let's say, 80 kilometers, it's prudent to build a DC system than an AC system. While if our wind farm requires a transmission system that spans over, let's say, 20 odd kilometers, it is prudent to build it on AC. So now I will show you the transmission network in Pakistan, but before I do so, we need to understand the geography. geographic elements are among very key considerations when we are planning our transmission networks. So Pakistan can mainly be divided into three regions. We can say to the right of this line we have the northern region, then mainly comprising of Sindh and some parts of Punjab. We can say that to the left of this line is the southern region. In the middle we have the greater area of Punjab. Now this is our central region. So how our transmission is planned is that to the very north we have our hydro resources. In the central we have our major load centers. By the way, this is Lahore over here, and the areas surrounding Lahore are among the greatest consumers of electricity in Pakistan. To the south in Sindh, somewhere around here, we have our coal based local generations that are currently producing at around 3000 megawatts. Okay, so the basic idea is that we have our hydro resources here, we have our coal resources here, and we have a major load center in this region of the central part of Pakistan. So when we'll see the transmission network, this would corroborate with these facts. So this is the geographic map of the transmission network in Pakistan. I would first run you through the keys. In red we have our 500 kV network. In green we have our 220 kV network, and this graph by the way only shows our primary transmission network, which comprises of the voltages above 220 kV, okay, and the voltages below 220 kV in Pakistan are called the secondary transmission voltages, which are not shown in these map. So one very apparent thing is the lines in red. This is our 500 kV network. In our transmission lexicon, we call it the backbone of Pakistan. So if you see, it starts from the very north and terminates in the very south. Okay? And throughout the center of the country, these lines continue to move. So we can see that there is a greater concentration of these red areas in the central part of Pakistan. These are our major load centers I was referring to, and these mainly comprises of the areas of Lahore, Faisalabad and Multan. If we look down here, this is our local coal corridor. Most of our local coal generations, rather all of our local coal generations are placed here, while to the north we have our hydro resources. So the function of our transmission system is primarily to deliver power from the southern coal corridor and from the northern hydro corridors to the central part of Pakistan where the load concentration is high. Okay. One very interesting feature of our transmission network is this line in pink. This is our 660 kV line commutated converter based bipole DC line. Okay, as we discussed in the previous slide, when we surpass the break even point, which is somewhere north of 800 kilometers, the feasibility of installing a DC line becomes high. So this is quite a feasible project which takes power from the southern coal corridors to the central load centers. So after discussing the type of transmission networks, let's talk about the power triangle. So I am reopening our mind map. We want to reach here. This is the goal that we established in the start of the presentation, and now we will work on the first important topic in this connection. These will be the topics that we'll be covering in this portion of our presentation. So let's begin. So in this slide, we will see what happens when voltage is applied across a few different kind of loads. So basic electrical engineering tells us that there are three different kinds of loads. First, we have resistive. We could either have a capacitive load or we could have an inductive load. Okay. And for all practical reasons, there are no pure loads. It is either the combination of this and this, as in a combination of resistive and capacitive, a combination of resistive and inductive, or a combination of all three, right? So in this case, we have a pure resistive load here. We have a resistive plus inductive load here, and a resistive plus a capacitive load here. Okay. Now our configuration is something like this. This is for our friends who are, let's say, not from the electrical engineering background, that we have applied a voltage source or a generator across a load. Okay. And this load could either be one of these three. It would introduce a voltage V here, and because of this voltage V across these 2 points, the current I would flow in this direction. So what happens when the load is purely resistive? We see that our voltage and our current waveform starts at the same point. They achieve their maximum value at the same point, and then since it is alternating current, it comes back to 0 at the same point. We call these two waveforms to be in phase. Okay, this is because they have no phase difference. We will just talk about the phase difference when we go into the discussion of RL or RC circuits, or in other words, inductive or capacitive circuits. So what happens when a current is passed through an inductive load? Okay, we will see that in our middle diagram here. Right. So it is very apparent that our voltage signal in red starts before our current signal in black, and the difference between these two is an angle phi, right? So we make two generalization from this, that when the current is passed through an inductive circuit or inductive load, the waves of currents and voltages are not in phase. Okay, and they are separated by a phase difference of phi. Okay, we can also make a generalization here that the current is lagging the voltage. Current lags voltage. Okay, and using the phase difference we study, we find out the power factor in this particular circuit to be cosine or cos of the phase difference phi. Okay, another generalization would be the fact that in inductive load we have a lagging power factor. Now this might be a rudimentary detail for people with electrical engineering background, but it is vital for all of our participants to understand this concept. Okay. Now when we move to the capacitive loads or the capacitive circuits, we see that our current waveform starts before the voltage waveform. This is a little truncated, so I will take a liberty and complete this wave. So we see that our voltage waveform is starting at this point, okay, and our current waveform is starting at this point. The difference between these two is also phi, and all the principles studied in the inductive load holds, except for the fact that in capacitive circuits we make these generalization. Number one, current leads voltage, okay, and the second one is that the power factor is said to be leading, okay. So the idea of discussing all these three kinds of load is the fact that if we see these three circuits in moving forward in our presentation, we will be able to identify which one of them is resistive, which one is inductive, and which one is capacitive. So whenever we will have a resistive circuit, we will have a phase difference between the two waves as 0 and the power factor is 1. So power factor will give us this idea. So whenever the power factor is 1, we will have a resistive circuit. Whenever the power factor is lagging, we will have an inductive circuit or inductive dominated circuit. And when we will have a leading power factor, we will have a capacitor dominated or a capacitive load. Okay. So in this way we will be able to identify these three different kind of loads moving forward. So having discussed the concept of phase difference in the previous slide, now let's get on to the slide where that concept will come in handy. Let's talk about active power. What is the active power? It is the power which is consumed by the load or is converted or dissipated in an electrical circuit producing useful work. So when you turn on a light bulb, a big portion of your total power would be consumed by the bulb to give light. This is the active power. This power is essentially the power for which we are given our energy bills, right? So the formula for the active power is that it's the product of voltage, currents and cosine of the phase difference that we studied in the previous slide. This factor, the one we were talking about phi, it is the cosine of this very angle, okay. So the same is explained here, that active power is measured in watts, it is the product of voltage in volts, currents in amperes, and the cosine of angle between the voltage and current, which is also called the power factor angle or the phase difference. Also, a very important thing to note here is that the cosine of angle phi, as we discussed previously, is called the power factor. Okay. So now we move on to the concept of reactive power. Reactive power is the power which by definition oscillates between the source and the load. So let's say when you turn on a device which is predominantly inductive, let's say we turn on the motor, it would require certain reactive power to work, okay. This power is in turn provided by some other elements which are rather capacitive in nature, like your generator when it's excited, or your capacitors. If the system lacks this power, it could lead to voltage collapse or reactive voltage issues, right? This reactive power is given by the formula that it's the product of voltage and current like the active power, but the very important distinction is that it depends on the sign of the power factor angle or the phase difference between voltage and current. Another very important distinction here is that unlike the active power which is measured in watts, the reactive power is measured in volt ampere reactive, which is often shortened down as a term var. So the next important type of power in this regard is the apparent power. By definition, it is the product of the total current and voltage in the system, right? So if we see its formula, we see a very important characteristic here. It does not depend on the difference of the phase between either the current or the voltage, but rather a direct product of their magnitudes, right? A very good example to visualize in this case is let's say a glass of your favorite fizzy drink. So when you see that glass from the outside, you see the total magnitude of the glass, right? Of course, some part of it is just the fizz, okay, that produces, let's say, no real taste in your glass, while there is some actual liquid here, right? So, as per this analogy, the actual liquid that we consume is the real power, the active power, while the fizz on the top is the reactive power. Why, on the other side, the whole magnitude of these two would give you the apparent power in your system. The apparent power is measured in volt amperes, and your system rating or the rating of some specific equipment is often measured in its VA or MVA, which is essentially its apparent power. So in this slide, we will try to understand the mathematical relationship between the apparent active and reactive power, which we studied in the last three slides, right? So mathematically, these three powers form a right angle triangle, which is called the power triangle, okay? The base of this power triangle is the active power, forming the vector Vi cos phi, okay? The perpendicular of this triangle is given by the reactive power, or the product of voltage, current, and the sine of the phase angle difference between voltage and current, okay? The hypotenuse of this power triangle is the apparent power, while the angle here is the power factor angle or the phase difference between the voltage and current, right? So using our trigonometric knowledge, we can redefine some of the formulas that we studied in the previous slide. The apparent power, which we said was the product of total current and voltage in the system, right? And we studied that active power is essentially the product of voltage, current, and the cosine of the angle between them, right? So this relation translates to we substitute the value of IV, which is the apparent power S, and it would be multiplied by the cosine of angle phi, which is essentially the power factor. So the active power would be the product of your apparent power S and the power factor, while the reactive power here would be given by the product of your apparent power S and the sine of angle phi, okay? Now when we have to find out the value of S from the values of P and Q, that is the active or reactive power, S is given as the square root of your active power and the square of the reactive power. Okay, this would give us the magnitude of the apparent power. Okay, and let's consider a very important thing here. We said that if our power factor is lagging, it is considered positive. When the power factor lags, phi is positive. Okay, and this would be the case of inductive loads. While when the power factor leads, then phi would be negative. Okay, while this load is going to be capacitive from what we discussed in the previous slides. Okay, so in case of phi is positive, our reactive power would be facing the north side. Okay, just like this triangle. However, when our power factor is leading, or when there is more capacitor element in the circuit, our reactive power would be facing south like this. Okay, and the apparent power would be given like this. Okay, so in this case the phi would be from in the clockwise counterclockwise direction, it is negative. So if we take the negative angle here in the counterclockwise direction, this would give us a negative phi. Okay, so this is going to be our S, this will be our Q, and this would still be the way we have given our P in the previous example, right? So the negative power factor angle would have no impact on P. However, the direction of Q would be reversed in due to our trigonometric considerations, right? Another important formula over here is that we said that our power factor equals cos of angle phi, right? So we can also say, because of our trigonometric relation, that cos phi is the ratio of our active power P and our apparent power S. Okay, so this is another important mathematical relation that we'll be using moving forward. Now, to understand the concepts that we learned in the previous slides, let's solve an example together. We have a system in which we have 9 megawatt of active power. We have 0 megawatts of reactive power, and our goal here is to find the apparent power S and the power factor. Okay, so let's solve this question together. The formula for the apparent power is S equals active power, which is P squared plus the reactive power Q squared. Okay, so this would translate to the root of 9 squared plus 0 squared, essentially becoming 9 MVA. Okay, and we also learned in the previous slide that the power factor or the cosine of phi equals due to the trigonometric considerations that cos of this angle would be base over hypotenuse, so essentially becoming P over S, and in this case we have 9 megawatts of active power and 9 MVA of apparent power, resulting in 1. So this cos of phi, or the power factor, would be 1. So we learnt in our previous slides that whenever the power factor is 1, our load is resistive. Okay, this solves our question. Now the example 2 here is a similar example using all the concepts that we have studied in the last 4 slides. Now I would request all the participants to take 10 minutes and solve these questions, and then we will discuss it together. The answer of this would be uploaded on our Google Classroom link. Okay, so please solve this example and submit your answers on the Google Classroom link. Okay, take 10 minutes for this question. So now let's solve this example together. So initially we have 9 megawatts of active power and 9 megawatts of reactive power. So our apparent power would be equal to S equals 9 squared, the active power squared and the reactive power squared. Essentially, this becomes 12.728 MVA. Okay. Our power factor in this case would be the active power over the apparent power, which is 12.728. This works out to be 0.707. Now, a power factor of this magnitude is often considered detrimental for the system, and the grid codes do not allow it. So, by the way, I skipped this very important next point. Since our reactive power is positive, it means that it is being consumed by the load itself. Okay. So this load which consumes reactive power is the inductive load. So this system is predominantly inductive. So to improve the power factor of an otherwise predominantly inductive load, we would add a capacitor, and in this case we added a capacitor of 6 megawatts. Okay. So what happens? Our Q new would become what the Q was previously before applying capacitors, which is 9, and then we added a capacitor of 6 megawatts, which essentially means that this megawatts would be provided to the system. So essentially this 6 megawatts mean minus 6, since it is being supplied to the system as opposed to being consumed. Okay, so this becomes 9 minus 6 equals 3. Okay, and now we will find the new apparent power. Okay, this is the power after applying the capacitor. This becomes 9 squared plus 3 squared and works out to be 9.487. Okay, and our new power factor would be the active power, which is 9, divided by the new apparent power, this. Okay, so 9.487, and this works out to be 0.95 lagging, because the reactive power is still consumed by the system in the order of 3 megawatts. Okay, but now this limit of 0.95 is a good power factor. Okay, so adding the capacitors to the system has improved the power factor. By the way, another announcement here is that this assignment we solved is going to add as a bonus score to the quiz that we will be solving in the end. Let's move forward. So before proceeding further, I would request the participants to pay a little more attention, because now we'll be switching the next gear. We'll be discussing slightly more advanced concepts, so your attention in this regard is needed. Our next topic now is how the transmission system is represented by the power system engineers. So the power system is represented in the form of what we call single line diagrams. What do these single line diagrams show? Primarily we show it with the help of generators, the load, the transmission line, okay, And now these components are connected through what we call the buses. Buses are essentially the grid stations. Okay, so if we see here, we have a bus on which the generator is connected over here, and then this bus connects the transmission line. Okay, this transmission line is in turn connected to another bus over here. Okay, and then it is stepped down using a step down transformer. Okay, and after stepping down, the load is connected through the transformer from another bus. Okay, now we talk about some other terminologies. We have a sending end voltage here. The sending end voltage is essentially the voltage at the bus on which the generator is connected, while the receiving end voltage is where the other end of the transmission line is connected. Okay, and on these transmission line we have some flows. We have our active power over here, we have our reactive power over here. Okay, this is the power active and reactive on the sending end, while on the receiving end we also have the same value, these quantities of active and reactive power. Okay, the voltage at the receiving end is called the receiving end voltage, represented by VR. The voltage at the sending end is the sending end voltage Vs. These are some standard terminologies that we will be using further once we see our analysis and the system itself. Our next topic is the per unit system. So up till now we have covered the power triangle and three different type of powers and the phase difference. Okay, this box is checked now. The next topic that we'll discuss is the per unit representation of the power system. So, per unit system is a convenient way of representing the system quantities. Okay. The idea here is that we make a quantity our base quantity, okay, which is, let's say if we are talking about a voltage, we select a certain voltage to be our reference or the base value, and whatever is the quantity that we are obtaining, we divide it by the reference value and essentially get what we call a per unit quantity. Okay. When we will see the example of it in the next slide, it would make more sense, but the general idea of using per unit system is that the suspect values are identified easily, okay, and they make our calculation simpler. Okay, some standard per unit quantities that we use in our analysis are represented over here. Okay, so if we are taking, let's say, our power, when we are seeing the power as PU, it is essentially whatever the value of power that we are obtaining S divided by the base value of S. Okay, and similarly we have values for VPU or the voltage in per unit, the current in per unit, and the impedance in per unit. Okay. So, to build our understanding of the concept that we studied in the previous slide, we would solve this example. Okay. This example asks us to convert all the values of voltages in per unit system. Okay. So, now a little about this system, that it has one generator and a load connected to it, and this system is 132 kV system, right? Now we will select the value of our voltage base. So our base voltage or VB is selected to be 132 kV, this is something which we have discretion over. We are selecting 132 kV value of the base voltage ourselves. Okay. Now, when we look into our system, we have a value of sending end voltage as 132. Okay. So what would be the value of Vs in per unit? It would be whatever value we are obtaining here, which is 132 kV, divided by our base voltage, which is 132 kV. Okay. So this simplifies to 1.0. So we can say at the sending end we have a Vs of 1.0 pu. Okay. Now when we look at our receiving end, due to certain factors, our voltage has dropped to 125 kV. Okay. So the value of pu at the receiving end would be in per unit as 125.4 divided by 132. This essentially comes out to be 0.95 pu. Okay. So if we in this system, which is essentially 132 kV, we come across some voltage which is, let's say, of the order of 25 pu, we would easily identify this to be something deviating from the norm and to be an extraneous value. So in this case, the values which are inconsistent are easily identified. Okay. Now let's do vice versa of this example that we did. Let's say we were given a base value of voltage to be 132 kV, while our per unit value at that instance was 0.95. How would we obtain the value in kilovolts? Okay. So what we would do is we would multiply our per unit value of voltage with the base value. Okay. And this would give us our value, what we call V actual. Okay. V actual, or the value in kV. So multiply 0.95 with 132 kV, which is our base voltage, we would get 125.4, which is essentially the receiving end voltage. Okay. So the purpose of this was to show that any given the base value of any quantity, we can convert a per unit value into the actual value and any actual value into a per unit value. So now we'll move ahead. So now we'll talk about the model of transmission line, or how is it modeled by the power system engineers. So up till now we have discussed these topics that I'm highlighting, and we are actually getting very close to our target. So the next topic that we are going to discuss is here, which is the transmission line model. So our mechanism here would be that we would try to model our transmission line in a system in PSSC and then see that how would the model look like. Okay. So instead of drawing the model first and then modeling it in the simulation software, we are going to take the other route. Okay. So to understand this, we have made an example that a generator is directly connected to the load and the load is resistive. So to understand this, we have developed a model in which a generator is connected directly to the load. Okay, and we will see that how the system behaves. Okay, so the given is that a generator which can generate up to 240 megawatts is connected to a resistive load at 140 megawatt. So essentially this means that this load draws no reactive power, or the system therefore would not produce any reactive power in this case. Okay, so we have done this analysis, done an analysis on a global simulation software, that the snippet of which would be showed now. So we see here that the generator feeds the load which is consuming 140 megawatts and 0 megawatts. Okay, and the generator is supplying that 140 megawatt to the system and producing no watts because it is not required by the system, right? Okay. Now we will move to the next slide, in which we have added a 30 kilometers 102 kV transmission line in the same problem. We will see that how this addition of transmission line would drastically change the results. Okay, so this is the output of our simulation tool. We can see here that a transmission line of 30 kilometers, on, by the way, a conductor called rail has been connected. Okay, we can see that the load demands 140 megawatts and requires 0 megawatts. Okay, this is the same load which we saw in the previous slide, right? But when we look at the things at the sending end, they get a little interesting. We can see that 142 megawatts are being supplied by the generator. Okay, so that means that when 142.6 megawatts were supplied on this line, we only got 140 megawatts on the receiving end. Okay, so about 2.64 megawatts were lost. It means that the transmission line must have something that would make the line lose some power or some real power. Now we know from our undergraduate courses in power system that the real power losses are because of resistance. Okay, so one parameter that we can take out from this example is that our system offers certain resistance. Okay, now we look at something more interesting. The load was strictly resistive, that it demanded no reactive power. But when we see our generator, the generator is producing 11.97 megawatts. It means that something in our system is consuming this reactive power. Something is acting like an inductor. Okay? And in the previous slide, when we saw our system, it essentially consumed or produced no megawatts. So that means the transmission line must be consuming some megawatts. Okay? Now we'll move to the next slide. And in the next slide, we have reduced the load. Our load is now down to 14 megawatt from the previous 140 megawatt. And now we will see how this line behaves. So our simulator shown that, okay, and after reducing the power flowing in this line, the resistive power losses have become very small. Okay, the generator is producing 14.1 megawatts while the load is demanding only 14 megawatts, as I mentioned previously. Okay, the load is still not requiring any megawatts or the reactive power because it is strictly resistive. But something interesting has happened. Now this generator is consuming 1.44 megawatts, which means that something in this system is producing the megawatts and it's not the load as we saw in the previous examples. Then it means that a transmission line must be producing these megawatts, and since nothing else is consuming these megawatts, the generator is forced to consume back these megawatts. So this becomes a mystery. In the previous slide we show that the transmission line was producing megawatts. In the previous slide we saw that the transmission line was consuming megawatts, and now in this slide we saw that the transmission line is actually producing megawatts. So we can say that the transmission line must have some resistive element, it must have some inductive element, and it must have some capacitive element, and they would become dominant due on certain conditions that we will see in the upcoming slides. So based on our discussion, let us now draw certain conclusions. So we can say that a transmission line could be modeled with a resistance R, reactance S X, and susceptance B. This susceptance B is essentially the reciprocal of the capacitance. So you can make a model of a line using resistance, reactance, and capacitance or its reciprocal susceptance, right? Now let's see this again. So when a current is flown in a line, it faces some resistance. Okay, this resistance is responsible for the active power losses in the system. Okay, but also from a fundamental physics course, we know that when a current flows on a line, it produces a magnetic field. Okay, and this magnetic field is due to the reactive inductance. Okay, also when we are applying a certain voltage on our transmission line, okay, it becomes charged, and when these two charged things are in close proximity of each other, they act as a capacitor. Okay, so our one line can have a capacitance with the other line because both of these are charged. Both these lines also have certain capacitance with the ground, which is essentially on another potential which is 0. So these three components, that is the resistance, the reactance due to the magnetic field, and the capacitance which produces susceptance in the system, could be used to model the whole transmission line, which is something we can see here. So a line is represented by its resistance, the inductive reactance, as well as the capacitance. Okay, this is how we model a transmission line. So now we will discuss one of the most important features of the transmission line. This feature basically dictates how the transmission line is loaded and how it behaves. This feature is called the surge impedance loading. But let us see where we have gotten right now. We have completed our discussion on the power triangles. We have covered the per unit system. We have covered the transmission line model. Now we are down to the last topic before we could discuss the transmission capacity limits. So fasten your seat belts. So what is surge impedance loading? So we saw that transmission lines acts as sometimes as a capacitors and other times as an inductor. Okay, So which essentially means that at times it is producing wars, while at the other times it is consuming wars. Okay. So what happens when the wars produced by it equals the wars consumed by the transmission line? This is essentially the phenomena that we are going to observe in this section. So the definition says that the surge impedance loading represents the maximum power that can be transferred through a transmission line keeping a flat voltage profile. It means that if we have a voltage at the sending end and at the receiving end, when the line is loaded at the surge impedance loading, so this is our sending end and this is our receiving end, and when we load our line at the surge impedance, our Vs is going to be equal to Vr. Okay, so the sending end and receiving end voltage would be the same. So what is the formula for surge impedance loading? It is given by the square of voltages divided by something called the surge impedance. Here Z naught can be approximated by the formula given in the slide. Basically Z naught equals to the square root of the inductance of the reactive inductance and the susceptance. Okay. So once we find the Z naught based on a particular voltage, we can find the surge impedance. And now I would like to restate another fact that we have mentioned below, but as a key pointer we would reiterate it. If the actual flow is less than the surge impedance loading, then the line would be producing wars and acting like a capacitor. Okay, but when the actual flow of power is greater than the surge impedance loading, the line would be consuming wars and acting like an inductor. Okay, now in order to understand the idea of surge impedance loading, we will solve an example. So for this particular case, an 100-kilometer line is connecting a load with a generator, right? And the parameters for X and B in per unit are given. We are also provided the base power, okay, and the base voltage, right? So our target here is to figure out the surge impedance loading of this particular line. Okay, so we began by finding the value of Z naught. Okay, so using this formula I just highlighted, we would find Z naught in PU. So Z naught equals the square root of x over b, and the x here is 0.65 0.06588, okay, while b here is 0.01572, okay. So in per unit system, this solves to be 2.04715 per unit. Okay. Now we have the value of Z naught but in per unit. In order to convert this per unit value, we would use the per unit convergence we studied previously. So in order to find Z naught in ohms or actual value, we would first have to find the Z base, and the Z base equals, as provided in the question, V base square divided by S base. For this particular question, we have been provided the values of uh, base voltage here, that is 132 kV, and base S here, or base power here, which is 100 MVA. So this becomes 132 K squared divided by 100 M. Okay, and the answer of this would be in ohms. This solves to be 174.24. Okay, so now we have the value of Z naught and Z base. We can find Z in ohms or Z naught in ohms. This solves out to be, using this formula, to be 174.24 times 2.04715 as given here. Okay, and the value of Z naught would be 356.696 ohms. We would put the value in this formula. We have V as 132 kV and Z naught as 356.696. Let's see what our answer comes out to be. So, doing the mathematics, we have 132K squared divided by 356.696, and this equals 48.84 megawatt. So the surge impedance loading of this line is 48.84 megawatt. So what does this signify? When we would load the line at the surge impedance loading, that is 48.84, the sending end voltage and the receiving end voltage would be the same. But below the sending SIL, if the line is loaded at any point below 48.84, we would see that the receiving end voltage would increase. Okay, while the vice versa of it is true, that if we load this line over 48.84, we would see that the receiving end voltage would substantially decrease. This is something we will try to prove from the simulations that we have shown in the coming slides. Okay, so in our simulation that we did on the power simulator, we first loaded a particular system at 184 megawatt. By the way, the line that we are discussing has a characteristic. For the sake of simplifications, and which is often the case with a power system, the X of a transmission line is more pronounced than its R. So in this particular case, to get more, let's say, easily interpretable results, we have selected a line whose resistance is extremely low and could be neglected. Okay, so now let's see our power system simulations. So we have applied a load of 185 megawatt to a transmission line connecting a generator. Okay, this load is resistive and therefore consumes no reactive power. However, due to the characteristics of this line being loaded above its surge impedance loading, which we found as 48.84, this line is consuming megawatts. Okay, so therefore we see, because of this consumption of megawatts by the transmission line, there is a drop in voltage at the receiving end. The receiving end voltage is down to 0.9 per unit or 120. Okay, while the sending end unit shows that the generator here is producing 81.81 megawatts. Okay. Now this is an example of when a line is loaded above its surge impedance loading. So in the next example, we will reduce the loading of this particular line drastically and we will see what happens. So in this case, we have a load of 2 megawatts being passed by this 132 kV transmission line. Okay, what we can see here is that the load is resistive and therefore does not consume any megawatts. However, we can see that this line is supplying minus 10.36 watts. So the minus signs show that this generator is basically absorbing 10.36 megawatts. And since the load is not producing it, then it must be the transmission line that is producing these watts. So what happens at the receiving end? We can see that our voltage is now up to 134.25 kilovolts. Okay, so this is greater than the sending end voltage. What does this signify? This means that when the line is loaded below its surge impedance loading, the receiving end voltage increases, and this is because of a phenomena called the Ferrante's effect. Okay, so when the line is producing watts, the voltage at the receiving end increase. This is our, let's say, a key point to remember moving forward. Okay, but in both of these cases, the common factor is that the sending end voltage and the receiving end voltage are not the same. Now we will load this line at the surge impedance loading, as can be shown in the next slide. So we loaded the line at 48.84 megawatts. Okay. So this line loaded at 48.84 megawatts shows that the line is neither producing watts nor it is consuming watts, but the watts on both sides is essentially the same, which means that the voltage at the sending end, which is 132 kV, equals the voltage at the receiving end. Okay, so at surge impedance loading, the sending end voltage would be equal to the receiving end voltage. So on completion of this topic, let's take a 10 minutes break and we will restart in 10 minutes. Now, welcome back from the break. Let us commence our session. So, having discussed all the prerequisites, now we come to our main topic, the transmission capacities. Okay, so as you can see here, we have covered all the areas that were required to study the transmission limit. So, this big box has been completed. Now, let's come to our target of the day. Okay, that's the transmission capacity limits. So what is the transmission capacity? So transmission capacity could refers to the maximum amount of power that can flow in an electrical transmission network between two specific points. Okay, and the transmission or power capacity is limited by three important considerations: the thermal limits, the voltage stability limits, and the angular stability limits. We will cover all of these in the very same order. That first we'll cover the thermal limits, then we will go through the voltage stability limits, and then finally we'll talk about the angular stability limits. And there is a reason why this would go on in this order. So now let's discuss thermal capacity limits in details. So we know that when the power flow in a line increases, the current passing through the line also increases, right? And the increasing current has an impact that it produces more heat. From the fundamental physics, we have learned that when a material or a conductor is heated, it expands. Okay? And since the conductor is suspended between the two towers or the two poles, this expansion would cause it to sag further. So over time, once the conductor is heated beyond its recommended material limits, this expansion makes it to lose its strength. There could be instances when a conductor is overheated and it collapses or falls down. Okay? Therefore, each transmission line is assigned a thermal rating. Okay? And what does the thermal rating show? It shows the maximum current that could be carried safely by that particular line or the conductor. Okay? So, what is thermal rating in its very essence? It is the rating that which shows the power that a conductor can continuously flow without causing an overheating or material damage to the conductor. Now let's see this example. We have a conductor between the two towers here, right? Due to its very nature and gravity, this conductor sags when connected between the two towers. What happens when this conductor is heated? Okay, it would expand and sag further. What would happen here now, that the ground clearance, which was previously let's say slightly higher, would decrease to this point, right? And this decreased clearance from the ground could make it happen that it might come in contact with a tree or another object, causing it to fault. So this is also an issue that is caused once the conductor is, let's say, uh, more power is made to flow through it beyond its thermal limit. Now this is a standard table of showing the thermal ratings of various conductors at various voltage. First, we at 500 kV voltage, we have Greeley conductor. It can carry up to 806 amps of current and an MVA of 2793, right? Now let's just discuss another thing. When we talk about the 220 kV conductor at rail, okay, we see that it can flow 884 amperes of current, while the power reduces down to the level of 674 MVA. Why is it? Of course, the reason behind it is that the higher the voltage, the more power that can be flown through a conductor using the same amount of current. Okay, so this was something I was withholding to share right now. It was a concept that should have been discussed previously. Okay, but right now I would want you to focus on one thing. This brake conductor at 500 kV. This is something we'll be using in our next slides. I just want you to remember this number. Okay, the thermal rating of a quad bundle brake conductor at 500 kV is 2772 MVA. This number would come in handy when we will see some of our future slides. Now let's discuss voltage stability limits in details. So the voltage stability limits refer to the maximum limit of a power system's voltage beyond which the system may experience voltage collapses or instability. Okay, what is the voltage collapse? So if in a system such a condition occurs that voltage becomes so low that no further power could be transmitted. Okay, and since this particular area is feeding any other transmission line or a grid station, this impact starts to cascade. Okay, so if no power could be flown through it, it would not reach the next point, and therefore a cascading blackout could ensue. Okay, to prevent system from ever reaching to such a point, the grid codes prescribe certain tolerance limits in which the voltage can remain or could be maintained for stable and reliable operation. Okay, these limits are usually plus minus 5% of the nominal value. Okay, so in per unit we can allow the voltage to rise up to 1.05 per unit and drop down to 0.95 per unit of the nominal value. But these grid codes also in emergency circumstances permits certain higher band, which is called the contingency voltage band, in which the voltage can rise up to 1.0 pu and fall down to 0.9 per unit. Okay, but what causes this drop in the voltage? Basically, it's the lack of reactive power. So we discussed previously that the inductive loads require reactive power. Okay, and the lines that are loaded beyond its surge impedance loading also consume reactive power or require the reactive power. If we do not provide enough regulation through our generators or devices like capacitors, SVCs, STATCOMs, etc., then the receiving end voltage drops to a point where no further power could be transmitted and the voltage falls below the required levels. Now, to understand the voltage stability limits, we take help of a curve called the PV curve. So the PV curve, as apparent from its name, the power voltage curve, represents the relationship between the power transfer on a transmission line and the voltage at the receiving end substation. So what it means is that let's say we have a generator connecting a grid station, and that power is transmitted through a transmission line to the load. Okay, so what would happen is that as the load increases, every step of the load, let's say at 10 megawatt, it would show the power generated or transmitted by the transmission line, which is 10 megawatt, and at when the line is transmitting 10 megawatt, what would be the receiving end voltage of the grid, this grid station, right? So both these values are plotted on a graph, and we can see the point where the voltage collapse would occur. For example, if the power at any given instance is P naught, represented here, this plot would show on the y-axis that what is the receiving end bus voltage. Okay. Similarly, as the power increases, let's say up to the level of P max, here we would see the bus voltage represented on the y-axis. I would also like to bring this point represented here, which I am highlighting in green, represented by the voltage collapse point. What does this point implicates? This point shows on the x-axis the maximum power that could be transmitted, okay, and once we try to push power beyond this point, it would simply not happen, okay. This is because the power voltage here has dropped so low that no further power could be pushed through it, okay. Now over here we have normal operating point shown by the green spot here, right. So this power here represented by P naught is basically on the normal operating point of the voltage. If we see closely between the voltage collapse point and the normal operating point, we have something called the voltage stability margin. This voltage stability margin essentially means that if the situation ever occurs that our voltage drops further, we have some cushion before the collapse of voltage would occur, right? Now, had our system been operated over here at this point highlighted in black, what would happen? Essentially, this cushion for our, let's say, drop in power would decrease even further, even less. Okay, so we would basically lose our cushion, and any disturbance would quickly bring us to the point of the voltage collapse. Now I understand that these concepts might be slightly hard to grasp for especially the people who are learning them today. So in order to make them easy, we have created some examples on our system simulator. Okay. So we will basically run them through in the simulator and show the results here. We have created two scenarios. Both scenarios have something in common. Basically, a large generator connects 500 kV transmission line to a load, and this transmission line is a Drake conductor. Remember the one which I told you to remember in the previous slides on thermal limits? So, the first connection arrangement is that the line connecting the two grids, which essentially means the line connecting the generator to the load, is a 10 kilometers line, okay, on the Drake conductor. This is example 1. In the example 2, we will see that the length of this line has been increased to 100 kilometer. Okay, so we will see the impact of we will basically create a PV curve and try to see what happens when the length of line is increased. So what would this simulation do? This simulation would essentially continue increasing load here, okay, and when the load increases, it will also increase the generation here, okay, and for every step of increase in generation and the load, it would record the voltage here, okay, building a relation between this voltage and the generation and trying to show that what is the maximum limit between which we can transmit the power, okay. Okay, now this slide shows the PV curve of our first example returned by the power system simulator that we are using. On our x-axis, we have the power transmitted by the transmission line, and on our y-axis, we have the receiving end voltage in per unit. Okay, this is 1 per unit here, 0.75 per unit here. Okay, so let's try to interpret this graph. So for 700 megawatt of power transmitted through the transmission line, the voltage at the receiving end is 1.0, okay, which means that the receiving end voltage has remained within the tolerance band, as well as it is same as the sending end voltage. Okay. Now, if we see this point at 2800 megawatts, the receiving end voltage has fallen slightly to, let's say, a point 0.98 per unit. Okay. It is still pretty close to 1.0 per unit, which is the let's say the nominal voltage here. And if you recall from the previous slide where I requested all the participants to remember the thermal limits of a Drake conductor, we remember that a Drake conductor has a thermal limit at around 2700 megawatt. Okay. So if we try to recreate 2700 megawatt here, it would mean that 2700 is transmitted at some point which I have, let's say, drawn with a red line. So even beyond the thermal limits, we can see that there is no significant drop in the receiving end voltage. What it implies is that for short lines, voltage stability isn't the primary criteria. Okay, the factor that would limit the flow of power for short lines at high voltage would be the thermal limit, which would be a binding constraint here. Okay, on our screen now is our second case when the transmission line on the same Drake conductor is 100 kilometers. Okay, so what we can see here is that the whole world has changed drastically. We saw that our thermal limits were at 2700 megawatts, which would be somewhere here, but our voltage has collapsed way before it. Okay, so we can see that our voltage collapse occurs at somewhere near 1700 megawatt. Okay, also, as I said that the grid codes permit certain voltage bands, and that voltage band is 0.95 per U as the normal operating limit, while in emergency conditions we can come down to zero point 0.9 per unit of voltage. So we can see that 0.9 per unit voltage would be somewhere here. Okay, and in emergency condition we shouldn't push our power beyond this point. Okay, so we will have to limit, for normal operations we will have to limit our power here, which roughly comes out to be 2050 megawatt. Okay, so when our system is operating at 1050 megawatt, our voltage stability band or stability margin would be this. Okay. However, in any case, we will have to limit our power according to the grid code to points before this line. So essentially, we can safely transmit our power at around 1050. So what is the conclusion here? We saw that in short transmission lines, thermal limits were dictating or were the binding limits. However, for medium lines of the order of 100 kilometer are showing some different binding constraint, and the binding constraint here is the voltage stability limit, which is acting as a binding constraint. Okay. So the question so comes to our mind that how would we mitigate these limits, or how would we mitigate between these limits, and how would we improve the voltage stability? Okay, there are several ways of going around it. Since we see that our receiving end voltage drops, we need to provide it reactive power as discussed previously. How would we provide this reactive power? One way of going around it is to apply a capacitor here, maybe a switched capacitor or a fixed capacitor. Okay, we can also add a generator here which would provide reactive power at the receiving end. We could also connect devices like SVCs and STATCOMs. Okay, also what we can do is we can connect this to another grid station which is bringing power from another source. Okay, so there are multiple ways of going around it, but all these options have to do with the provision of reactive power. So the VARs would need to be supplied to the receiving end in order to uh, make our system voltage stable. Okay, so finally the last topic in our discussion on transmission capacity is the angular stability limits, right? Angular stability limits happen to be one of the most complex topics in the power system stability. However, our mode of learning this today would be through examples, and we will try to see how the angular stability limits impact the transmission capacity. So the fundamental of power systems tell us that the megawatt flow between any two buses is determined by the difference of the voltage angles between those two buses. Okay, what does this mean? Let's say we have a bus 1 and bus 2. Okay, on bus 1 the voltage is V1 at an angle of let's say delta 1. Okay, and while on the other end bus 2 we have voltage V2 at an angle of delta 2. So the power between that would flow between bus 1 and bus 2 would be given by this relation. What does this relation signify? It signifies that the power flow between the two buses is equal to the product of the voltages, that is V1 and V2, and the sine of the power angle. And what is the power angle? Essentially the difference of the voltage angles at the both end. So the power angle here, which is given by delta, equals delta 2 minus delta 1, which is essentially the voltage angles of bus 2 and bus 1 respectively, right? While in the denominator we can see that the voltages are divided by a reactance. This is essentially the reactance of the transmission line between the path. Okay, so the power that would flow between these two buses would be doubled if we install another transmission line here. Why is this? The fundamental of electrical engineering tells us that when two lines are in parallel, their reactance or their impedance becomes half. So that means that this vector would become x by 2 if two lines are in parallel, and essentially the power would become 2 times V1 V2 sine at an angle of delta divided by x. Okay, so what does this mean is that if we add another line of same parameter or same reactance, the power would become double, or if the power has to be increased, then the sine of the power angle should be 1. Okay, and this would happen when the power angle equals 90 degree, as sine of 90 equals 1. But here is the catch. when two generators are at the power angles of 90, as in their relative angle, the angle between them is 90, they are at the verge of losing their synchronism. Any angle increase beyond 90 degrees would make them lose the synchronism, and they would no longer be synchronized, which is they would no longer be moving at the same speed. Generally, we try to keep the power angle in the limits between 30 to 40 degrees. Okay. If the power angle is increased beyond this point, our system becomes susceptible to lose synchronism in case a sudden load change or disturbance occurs. Okay. Now consider the example as shown in your screen. As you can see, two generators are synchronized with each other at 50 hertz, right? But you can see they have a difference of 45 degrees in the angles between them, right? This is essentially called the rotor angle or the power angle. The terms rotor angle and power angles are used interchangeably. So the previous slides might have been a little hard to digest, especially for the people who are not really aware of the power system engineering. But fret not, we will try to interpret the results through an example, and this whole concept would become really easy. Okay, so we have a very long transmission line which is essentially 700 kilometers long, 500 kV line on Drake conductor. Okay, what it is doing is that we have a generator B here and we have a generator A here. Okay, generator B can produce power up to 1050 megawatts. Okay, and this generator is inexpensive. It makes commercial sense to transport almost all the power it can produce to the load here. This load is essentially 5000 megawatts of resistive load. We have taken resistive load to keep the system simple, right? While generator B here can produce power up to 6000 megawatt. However, it does not make commercial sense to take all the power from here, this being more expensive of the two generators, right? We have also made a bus in the middle of the transmission line. This is, consider it a grid station at 350 kilometers. However, for the sake of convenience, we have removed the load from this particular grid station to show you more clearly the impact of transporting power over a very long transmission line. What we would do here is that we would analyze this system for any potential angle stability limits or their violation, right? So after simulating this system, firstly we will see if there is an issue with regards to the voltage stability. Here are the results of the load flow. Our inexpensive generator, the generator B, is producing 950 megawatts. However, while reaching the load through our very long transmission line, we are only receiving 895 megawatts. Okay, while our slightly expensive generator, generator A, is producing 4104 megawatts to supply this load. Okay, but with regards to the voltage, let's see here. As we said before, that after a long transmission line, we have to add a compensation device. That compensation is being provided by the generator A. Therefore, the voltage after transmission from the long line is having a voltage of 1.0 per unit, right? While on the sending end before the long transmission line, we also have a voltage of 1.0 per unit. Okay, so that means that just by looking at this load flow, we don't see a voltage problem here. Okay, and that intermediate grid we talked about is also showing a voltage of 1.0 per unit. Okay, but now comes the main question: is this system stable? In order to check the stability, we will have to run a dynamic simulation. And how would this dynamic simulation work? Okay, firstly, we will run this system smoothly without applying any disturbance for 1 second. Okay, when a time of 1 second is reached, we will apply a fault at this bus. Okay, and this fault would be cleared in 5 cycles, which translate to 0.1 seconds, which is like a standard time for clearance of fault. And once this fault is cleared, we will run the system for 10 seconds to see if the system stabilizes. Here are the results of our dynamic simulation. Here on the y-axis we have relative rotor angles, which mean that the power or rotor angle of generator A, rotor or angle of generator B minus rotor angle of generator A is plotted on the y-axis, while on the x-axis we have time. As we can see, the fault occurred somewhere here. Okay, before the occurrence of fault, we had the relative rotor angle of less than 50 degrees. It means that the system was working smoothly and in sync. The both generators were perfectly synchronized. But when the fault occurred, we saw that our rotor angle continued increasing trend. Okay, and at this point, it crossed their relative angle crossed the threshold of 90 degrees. And as we said before, once the relative angle crosses 90 degrees, the generators lose their synchronism. And the same is shown with a plot. It, by the way, in technical terms, this is called first swing instability. That as soon as the fault occurred, the generators were unable to, let's say, align their angles and became lost their synchronism and became unstable. Okay, and this growing line is exactly showing that. But what happens if we limit the capacity of this line from 950 megawatt to 500 megawatt? What it means is that we have reduced the generation from our inexpensive generator B to 500 megawatt. Okay, and after incorporation of losses, 484 megawatts reached our load from the transmission line. The rest of the power is being generated by the generator A. Okay. Now we will see if reducing the power on this transmission line would keep the system stable. Here is our result. And indeed, limiting the capacity on the transmission line has actually helped to keep our system stable here. In the red line, we have our relative angles after reduction of load, while in the pink line, we have the result that were previously shown. So if we see here, when the fault occurred, our rotor angles continued increasing and becoming unstable in our first example. While when we reduced the transmission capacity, yes, there was a disturbance here, but this disturbance got cleared and the system became stable. Okay, so what does this signify? So let's try to draw a conclusion here. For very long transmission lines, even though the system appeared to be stable in steady state with regards to the voltage stability, it is not stable in the transient or dynamic analysis, particularly with regards to the rotor angle stability or the angular stability, right? And limiting the flow on that particular line would help us make the system stable. So the limiting factor for very long transmission lines is actually the rotor angle stability. Okay. So based on all three analyses, let's draw certain conclusions. For short transmission lines up to 50 miles, thermal limit appears to be the binding limit. That is, that the thermal limit would limit the capacity of a short transmission line. While in among the medium transmission lines, which have lengths of 50 to 150 miles, voltage happens to be the binding limit, as in the transmission capacity is limited by the voltage stability requirements. Okay. But for very long transmission lines that spans over 150 miles, it is actually the angle stability considerations that limit the transmission capacity. So this concludes our discussion on transmission. But before starting our next topic, let's take a small quiz. Please go to your Google Classrooms for the quiz. We will see you in 10 minutes. Welcome back from the quiz. Now let's recommence our session and conclude it with the last topic of the day, which is demand. So, in our next section, we'll discuss some techniques of how to manage the demand. Okay. Demand management in context of the electricity market is a very critical aspect that ensures reliability and efficiency in the electrical supply chain. It refers to the techniques that are used to reduce or control the consumption of electricity, reducing the peak demand, optimizing the resource utilization. From the perspective of the electricity market, it is vital for ensuring grid reliability, cost efficiency, environmental sustainability, and bringing overall energy system optimization. It is often said that it costs way less to save 1 megawatt of energy than to produce another megawatt. So, in this context, it is vital. Okay. Also, the demand management measures enable the consumers to make informed choices, while at the same time it helps the utilities and the grid operators to manage and balance the electricity in the grid effectively. So, in our session today, we will discuss only two demand controls method, which are namely the demand response and the energy efficiency. Now, let's see how these measures of demand control impact the overall energy economics. We know that our peakers often cost more to us to run. Okay, so as we can see here, the peaker plants takes around 20 rupees per kilowatt hours to produce a single unit. Okay, we have prices on a y-axis and we have megawatt quantity on the x-axis. The blue line here is showing a supply stack. Okay, it is often said that electricity demand is inelastic. Okay, which means that in short term the demand stays almost same or constant. And if we draw a demand curve here showing inelastic demand, we would see that the marginal cost of our system would become 20 rupees per kilowatt hour. However, if we say that we introduce certain signals in the market that would make this demand slightly elastic, the results would change. This dotted line shows if the demand was inelastic, right? And if we can see here that the equilibrium price or the market clearing price has decreased, and this is because we are no longer using the peaker plants. In the times when the peaker plants were needed, we, instead of running those plants, we curtailed our demand by giving a price signal, let's say. So in this way, demand control methods help us reducing the energy prices. So the first method of demand control that we are going to study today is demand response. What is demand response? Demand response represents a set of solutions that are deployed with the goal to change the peak load of electricity consumption. Okay. So the first idea is to reduce the peak load, while the second idea is to keep the energy consumption over a longer horizon the same. So it means we are reducing the peaks while we are ensuring that the overall energy consumptions remain the same. Let's try to see this concept graphically. Let's assume that our demand profile looks something like this. Okay. What we would want to do with this demand is that we have a certain peak, this area which I am highlighting, okay, and we want to shape this area. So our first goal is to shape the peak or peak shaving, and then there are valleys right here where the demand is dropping. What we ideally want to do is that we want to fill this area. Okay, so we want our profile to look something more flatter, and that is done by shaving the peak and filling the what we call valley. Okay, and the idea here is to shave the peaks in the time when our system is more stressed and vulnerable. There are two main mechanisms to achieve demand response. We basically have two programs or two type of programs that are often used. The first one is price-based programs. These price-based programs gives price signals and tariffs to incentivize the consumer to shift their consumption from the peak times to the, let's say, off-peak times. While on the other hand, we have incentive-based programs, the purpose of which is to make direct payments to the consumers who shift their demand as the part of demand side response. Okay. So this slide shows the price-based and incentive-based methods of demand control or demand response that we will discuss today. In the price-based method of demand control, we have time of use method, real-time pricing method, and critical peak pricing method. Okay. While in the incentive-based programs, we have interruptible or curtailable services and direct load control. So the first price-based method of demand response is the time of use pricing. Under the time of use pricing, the electricity rate is divided into different period of time. Typically, we have higher rates during the peaks and the lower rates during the off peak. Okay, so we can see here we have different rate or lower rate during the off peak situation and the higher rate during the peak situations. Okay, what this would do is that during this time we will be shaving our peak. Okay, and during this time we will be giving a price signal that would basically encourage valley filling. Okay, so essentially this has two time blocks of peak and off peak, and the rate are given to the consumers in particular season. Okay, this program offers different rate of electricity price per unit in different block of time, and what these rate reflect is that the average cost of electricity is different in different periods of times. The next price-based method is the real-time pricing. In the real-time pricing, the consumers with are provided the dynamic electricity prices that change in real time, and they reflect the fluctuation in supply and demand. Okay, so the rates in this method vary continuously in a day and directly reflect the wholesale prices in the electricity market. This can be seen in the graph here, that the blue line continuously changes depending on whatever is the wholesale price. Okay, this program offers hourly price rates linked to the changes in real time cost of power. This scheme is ideal method to adjust the power balance between supply and demand and requires smart grid. Therefore, to implement such a program, we need to have a very robust infrastructure. Okay, and since this is a very robust scheme, it has profound impacts on the user's behavior, the way in which the system operations take place, and in the way in which the overall grid is managed. The third price-based method of demand response is the critical peak pricing. Okay, in critical peak pricing, the electricity rates increase significantly when peak occurs or when there is a period of peak and when the demand is exceptionally high and the system operator or the market wants to curtail the peak during that interval. Okay. So the critical peak time periods define the high specified per unit rate for usage during the load time. These programs usually occurs almost 6 to 10 hours in a season, and they have a relatively short time notice period in which the consumers are told that these prices would get higher. This is very similar to the time of use method, but adopts a much higher peak pricing when the system reliability is compromised or when the supply costs are very high. So our first incentive based method of demand response is interruptible or curtailable load. Interruptible or curtailable loads are specific type of demand demand response resources in incentive based demand response programs that can be temporarily interrupted or reduced. The signal for curtailment or interruption is sent from the utilities or grid operators during the periods of peak demand or grid stress. Okay, let us take a look at this graph. What it shows is that we were supposed to get a peak over here. Okay, but the operator sent a signal to the interruptible load, somebody who had let's say contracted for it, and that particular demand reduced its load here. Okay, and when we see this black graph at the bottom, we show that there is a demand response event in which 400 kilowatt was curtailed. Okay, the customers on the interruptible or curtailable service tariffs receive a discount or bill credit in exchange for agreeing to reduce their demand during the system contingencies. But what if these consumers do not curtail? Well, in that case, they can be penalized. Interruptible load users can sign contracts with the power supply companies, allowing them to break the power supply under different specific conditions. So the second method of incentive based demand response is the direct load control. Direct load control, or DLC, is a strategy that allows the utility or grid operators to directly control or adjust the operation of specific electricity consuming devices or appliances at the consumer premises. So basically, a consumer signs a contract or agreement with a distribution utility through which the distribution utility sends signals to the devices that are installed in the premises of the residential consumers, and the usage is metered. Okay, and based on the usage, the demand user is provided certain incentives. Okay, and this is done remotely through various communication networks and advanced metering infrastructure that enable managing the demand of electricity during the peaks period and grid emergencies. DLC is operated to avoid peak time electricity purchases by the distribution utilities, and these programs are voluntary, so the consumers are not penalized if they don't accept the offer. So now we will discuss our second methodology for demand control, which is energy efficiency. Energy efficiency plays a critical role in demand management by reducing the overall consumption of electricity without compromising the desired energy services during peak and off-peak conditions. Achieving energy efficiency requires a comprehensive understanding of devices that influence the overall efficiency and employs various methods to optimize their performance. So, the idea here is that we try to optimize the performance of devices that are already installed, either by using it with certain other devices or by replacing them altogether. So the energy efficiency measures lower the baseline electricity consumption of the consumers. Energy efficiency measures to seek to minimize the energy waste and maximize the output of energy services and reduce the need for additional power generation. So the idea here is to limit the generation expansion and instead focus on optimizing or maximum utilization of what is already there. Now we'll discuss the methods of how energy efficiency programs are designed. The first thing is the energy efficient design. These employs the techniques that are involved in using advanced technologies, material and engineering techniques to reduce the energy losses and to maximize the energy output for a given level of energy input. The next is energy management services. Implementing energy management systems such as smart grids and smart meters allow for real-time monitoring and control of energy consumption. This helps to identify energy inefficiencies and allow automated load adjustment during peak demand periods. So, the idea here is to use advanced infrastructure to first monitor the consumption and then to automatically adjust those consuming devices. The third is the high efficiency appliances and lighting. This means that when we have old and inefficient appliances, we replace them with high efficiency devices. An example of this could be replacing the old incandescent lights with new and efficient LED lighting, and this would provide essentially the same usage output for the lesser energy input. Another method is to conduct energy audit and efficiency and carry out efficiency measures. So, the first we need to conduct energy audits to assess energy consumption pattern and then identify the opportunities in which inefficiencies could be removed, right? Implementing efficiency measures based on audit findings can lead to very targeted energy savings. The next method to achieve energy efficiency is industrial process optimization. When we are in an industrial setting, optimizing the processes and equipment could lead to significant savings in energy. This may involve improving the production efficiency, reducing energy intensive processes, and adopting energy efficient technologies. Lastly, we have behavioral changes which are often the result of certain education. So the idea here is that we raise awareness and educate the consumers and employees working in the industries about the energy efficient practices that can lead to behavioral changes that contribute to improved energy efficiency. Our last topic for the day is the benefits and challenges in implementing the demand control programs. So first, let's talk about the benefits of demand control programs. The demand control programs improve the efficiency of the energy system and help in improving the system load factor. Okay. It also reduces the financial needs to build new energy facilities through deferral of capital expenditure resulting from peak demand reduction. So when we have reduced a peak, we might not feel it necessary to install, let's say, another peaker plant. And since we are basically reducing our consumption, it also means that we are reducing the production of greenhouse gases which are produced as a result of burning fossil fuels. Okay. It also helps in lowering the cost of service to the consumers by lowering the generation cost and lowering the consumer bills through the use of energy efficient equipment and appliances. Also, the demand control programs reduce the power shortage and power cuts by improving the reliability of the system through decrease in demands during the peak situations when the power shortages might occur. Okay. So the demand control measures also help in improving the reliability and quality of power supply. Why this would happen? When the system is stressed, the demand is reduced, and when the demand is reduced, the reliability of the power system increases. Also, an economic benefit of the demand control programs is that it contributes to local economic development. It increases the employment through relocation of capital that is assigned to, let's say, the generation projects or otherwise high investment driven projects to the other social sector development programs. Finally, we will discuss the challenges in the implementation of demand control programs. Firstly, it is a capital intensive work. It requires large upfront cost because these programs require significant investments in the infrastructure, technologies and marketing. Marketing here is important because these involve basically teaching or educating the consumers to change their habits, right? And to do so, a lot of money needs to be kicked in this segment. Secondly, there is a chance of resistance coming from the consumers because some consumers may be reluctant to participate in these programs due to their privacy concerns or the fears about the change in their habits. Okay. Also, these programs are very complex and requires high level of coordination. Coordination for various demand control initiative, demand response events and energy efficiency program can be challenging for the people in the utilities and the program administrators. Fourthly, not all consumer may be willing to participate in these programs, and since such programs require high level of participation, limiting uh, the number of participants may impact the overall let's say benefits of these programs in reducing the peak demand. Another important factor or challenge here is that any kind of overestimation or underestimation in the demand control programs could substantially make these programs become suboptimal. Okay. Lastly, since these programs require high degree of engagement with the consumers, the success of it would actually come out when a large consumer base get involved with these programs, right? And this engagement could be very hard to achieve uniformly, as not all participants would want to be engaged in these programs. So with this, we have reached the end of our session today. I would like to thank you all for your participation. And now we will open the floor for questions that you have already posted in the chat box.